Okay, today we're doing some pretty important work. Polynomials, factoring is zero. So it's all about roots of polynomials. We've been doing this kind of work for a little while now. So in this case, like to solve this, to find the zeros, we just factor it. It's not too bad here. Let's see, 2 and 2 don't work, maybe 4 and 1. It's positive 3, so plus 4 minus 1. So the solutions would be at x equals negative 4 and x equals 1. So the connection I want you to make is really with the graph here as well. So a 0 of the graph looks like this. So it's where the y value is 0. So 1, 2, 3, 4. This is the x-axis and 1. So there's going to be a solution at negative 4 and a solution at 1. The ordered pair there would be 1, 0, and the ordered pair there would be negative 4, 0. And they're called zeros of the graph for a number of different reasons. The y values are 0 for both of those points. If I plugged 0 into this function for x, if I did like f of, or I plugged in negative 4, I should say, let's plug in 1, that's easier. F of 1 squared is, let's see, 1 squared plus 3 times 1 minus 4. You can probably do that. 1 plus 3 minus 4 is 0. So the output, when I plug 1 in, I get an output of 0. When I plug negative 4 in, if I plug negative 4 in there, I will get an output of 0. It's a 0 of the graph. So the graph would look, just a rough sketch of it. We talked about sketching graphs and end behavior yesterday. So you can see that this has a behavior of, it's even and positive, so it's got to be up for its end behavior. And so the graph's going to look, well, it's going to look like a parabola. You probably guessed that. And so those are the, that's what the graph, just a real rough sketch of the graph would look like. A couple other things about the graph I want you to kind of notice. I'm not sure where the axis of symmetry is, but it's pretty easy to find out. So you think about an axis of symmetry, it's got to be somewhere right there in the middle of that. So to find the axis of symmetry, if you just kind of like found the middle between these 2 points, there's 1, 2, 3, 4, 5 units. So if I went 2.5 units somewhere around right there, or you think about it, if you average negative 4 and 0, so negative 4 plus 1 divided by 2, that's negative 3 divided by 2, which is negative 1.5. So there's a dotted vertical line right here at x equals negative 1.5. It's right in the middle, 2.5 units from each solution, or 0 of the graph there. So it's all about finding the relationship between all those different kinds of points. Here, what's nice about this one is it's already kind of set up for us. So let's find the zeros of this graph. So let's sketch out all the graph. Oh, that's a really bad sketch. That's okay. So x equals 2 is going to be one of the solutions, or zeros. X equals negative 3. Certainly going to cross there at negative 3. And x equals 0, because we set each factor equal to 0, so that is a factor, so x equals 0 will be a solution as well. What's the end behavior of this graph? So the end behavior of this one would be, let's see, if I multiplied all those out, I'm not going to multiply, but I'm just going to look at the first term of each. X times x times x is x to the third. I know the first term would be x to the third power plus some other stuff here. I don't care about the rest. The largest degree term would be x times x times x, which is x to the third. That's positive and odd, so I know the end behavior would be down and then up. And so it's going to start down, it's got to hit that point. It's going to end up, it's got to hit that point on the right. So I know my graph looks something like that, which is nice. And we can make a sketch of the graph doing that. We'll get more into this more advanced stuff in a minute. So well, let's just try this. So let's try to make a little better sketch. Say I don't know what's going to happen between here. Maybe the graph kind of does this. Maybe the graph does this. Not sure, maybe. So we'll get more into multiplicity later, but let's just plug in a point in between those 2 points. So maybe I don't know what's going to happen. So I'm going to plug in -1 there. So an x value, anything between 0 and -3. So let's plug in -1 to this function. So we get -1 times -1 minus 2 times -1 plus 3. So we multiply that out, we get -1 times -3 times +2. Negative times negative is a positive, 3 times 2 is 6. So -1 comma somewhere right up here is our point. So I know the graph kind of comes up. I'm not sure if that's the tallest point, but it's got to hit that point and come back down. Maybe test a point in between these two. So let's plug in 1. That's between 0 and 2. So f of 1 would be, let's see, plug in, so it'd be 1 times 1 minus 2 times 1 plus 3. So this would be 1 times -1 times +4, which is -4. So 1 comma -4 would be another point on that graph. The graph looks like it goes down, then comes back up, something like that. And that's the actual graph of that graph. I'm just going to show you, I think I have it here, what the actual graph looks like. I'll try to grab that for you. So the actual graph looks like this. And you see our sketch is pretty accurate there as far as, got the zeros in the right spot, has some of those points in the right spot. That's what we're trying to do, sketch a graph without the use of a calculator here. So we didn't really need a calculator to graph that, and we did a pretty good job of sketching it. Pat yourself on the back. It's pretty good. Let's talk about multiplicity now. So multiplicity, some interesting things happen with multiplicity. So let's just talk about that for a second. So when you have a graph like y equals x squared, you probably know what that graph looks like. It kind of does this. It hits the axis at only one point. It does have a 0. The solution there is at 0, 0. But it only touches the axis in one point. And so anytime you have a graph that has the same factor twice, like let's try this one, y equals, we've done a lot of transformations this year. So if you have like x plus 2 quantity squared, we know that that takes that graph and moves it, let's see, 2 units to the left. So the 0 would now be over here at -2, 0, and the graph would look something like this roughly. So interesting thing is when this exponent is even, when we have an even number of factors, so like 2 of the same factor, 4 of the same factor, whatever it is, the graph is always going to bounce off the axis, right? And so the opposite is true for odd functions. So if you have something like y equals x to the third, you might know that function. We've seen it at least this year. Looks something roughly like this. Has a solution at 0, 0. And notice what happens when it hits the, well, because this is an odd multiplicity, there's like 3 of them, not 5 or 7 or 1, then this graph is always going to hit the axis and go right through the axis. So odd functions, when you have an odd number of roots, it's going to go through. When you have an even number of roots, it's going to bounce off because that's the behavior of the graph. So this is a really nice thing. So let's try this one. First, let's get the roots like we normally would. The root solutions would be at, let's see, -1 and x equals 3. So the roots are at, let's see, -1, x equals 3. So there's a solution there and a solution there. If I multiply this out, I know there's a negative out front, so I know it's going to be negative. X to the second power times x to the first power is x to the third power. I don't know what my next term would be. I don't care right now. But that first term would be negative x cubed. That's an odd. It's an odd function that is x cubed is that is negative. So the end behavior would be, let's see, that's going to start up and then end down. So the function here would look like this. It starts up, hits that point. It ends down, so it's going to go there. Now, there's two options in the middle here. Either it kind of goes up like this or down like that. So those are the only real two options. And multiplicity will help us figure out what's going to happen here. So this solution at -1, talking about this one, there's two factors there. The multiplicity is 2. When we see a multiplicity of 2, the graph always does this. It always bounces off. So it's going to hit this point and bounce off the graph. And then come back down and go through. So it goes through right there because this one is an odd power, so it's going to go through right there. Now, what I still don't know is, I don't know how high that bounces. So as a double check, it's not a bad idea to maybe plug in one value in between these two things. So I kind of know how big this graph is. So I'm going to plug in maybe 1. So anything between -1 and 3. So I'm going to plug in 1. I like plug in 1. That works. So this would be -1 plus 1 quantity squared times 1 minus 3. Okay, sorry about the interruption. So this would be -4 times -2, which is 8. So really this would 1, 2, 3, 4, 5, 6, somewhere up here at 1, 8 would be a point in this graph. So I should probably erase that a little bit and maybe figure out where it's going to go through that point and then come back down. I could also figure out the y-intercept, right, if you wanted to. That's another thing you can figure out. I think it would cross at 3 there. But you could figure that out just by doing the last term, 1 times -3 times -1 there up front would give you the y-intercept. So that's the basic idea of sketching the graph and doing that. I want to do one more kind of thing, which is working backwards again. So let's say we know the zeros. Well, if you think about this, like if you know the solutions at 3, the factor is x minus 3. The solutions at -1, the factor is x plus 1. So here we need to like work backwards. Can we write the factors for this function? So y equals, let's see, if solutions at 1, the factor would be x minus 1. Solutions at -2, that would be x plus 2. Solutions at 3, that would be x minus 3. The cadence there is always x minus the solution is the factor. So I've now written as a factor. It's almost a function. We really want to make it into a polynomial, so we want to multiply these together. So this is foiled maybe these two. We get x squared minus x plus 2x would be plus x minus 2 times x minus 3. And now we have to kind of like distribute every term here to there. So we'll like distribute the x's. So we get x cubed minus 3x squared. We distribute this x times that, so that would be plus x squared plus 6. Oh, sorry, that's not plus 6. My eyes go to a different spot there. So that would be x times -3, which would be minus 3x. And then -2 times x and -2 times that, so that would be -2x plus 6. Combine like terms here, we still have a y equals out front, so this would be y equals x to the third. Let's see, minus 2x squared minus 5x plus 6. So that is a polynomial equation. There's one possible polynomial equation. There are others. Right, a polynomial equation doesn't say the. That's one of the possible polynomial equations that would have roots at those values. So it's kind of just a situation of working backwards. Where we're almost thinking about the solutions and factors and working backwards to get that. That's the end of the lesson.